Welcome back, everybody, for another deep dive. And today we're going to be looking at a really interesting question.
Mm,
Is fundamental physics sort of stuck right now? We have this source material that argues that, well, it might not be like in a full-blown crisis or anything. Maybe things have been kind of spinning their wheels since the 1970s.
yeah.
So are you ready to dig into some of these big questions about the universe with me today?
Yeah, I'm ready. Let's do it.
Perfect. Now, this source material, right off the bat, it draws this distinction between a crisis in physics and then just a period of stagnation. What do you think? Why is that distinction so important? Does it tell us anything about how physicists are viewing this whole thing?
Yeah, it's a really important distinction to make. A crisis would mean that the models we have are just like fundamentally broken. They're contradicted by all these observations we have. But stagnation, it suggests that, well, we're putting in the effort, we're doing the work, but we're not really getting those huge paradigm-shifting discoveries, those ones that redefine the way we understand everything. And I think that's how a lot of physicists are feeling right now, a lot of activity, but
Hmm.
is it really moving us closer to these big answers to the big mysteries?
So it's less like a the sky is falling panic and more of a are we even on the right track at all sort of vibe.
Exactly. Yeah. And the source, it points to these specific problem areas that are feeding into this whole sense of stagnation.
Yeah.
One of the biggest ones, of course, dark matter. We know from what we've observed that there's a whole lot more mass in galaxies and clusters than we can actually see.
Yeah. The missing mass problem, right? It's
Yeah.
like you're trying to balance your checkbook, but you have absolutely no idea where all the money's going.
That's a great analogy. And it implies that something else has got to be out there, something we can't detect directly, but it's exerting this gravitational pull. And that's what we call dark matter.
Okay, so that's one puzzle. But then the source also talks about dark energy.
Mhm.
And that's a whole different thing, right?
Yeah, a whole different beast. Dark energy is this mysterious force that seems to be accelerating how the universe is expanding. Instead of slowing down like you'd expect as gravity pulls everything together, it's actually expanding faster and faster, like someone just slammed on the cosmic gas pedal.
So we've got this invisible matter that's holding galaxies together, and then we've got this invisible energy that's pushing everything apart.
Oh, man. No wonder some physicists are feeling stuck.
Oh, it's a challenge, for sure. And it gets even more complicated when we try to reconcile our two most successful theories of physics, right? You got quantum mechanics, that describes the world of atoms and particles, and then you got general relativity, which explains gravity and the large-scale structure of the universe. And those two don't exactly play nice, do they? It's like trying to mix oil and water.
It is. That's a good way to put it. The problem is they operate on such different scales and with different assumptions. Like quantum mechanics, it deals with this probabilistic nature of particles, while general relativity, that's based on the smooth, continuous fabric of space-time. Unifying these two, it's been a major goal, like the holy grail of modern physics, some would say.
And I've heard of like string theory. Are there other theories that are trying to kind of bridge that gap? It seems like none of them have quite figured it out yet.
Yeah, string theory, that's definitely one of the big players. It says that the fundamental building blocks of reality aren't these little point-like particles, but they're actually these tiny vibrating strings. And the different vibrations would correspond to different particles and forces. Then you've got loop quantum gravity, which takes a more geometric approach, suggesting that space-time itself is quantized. It's made up of these tiny little loops.
So those are like the big contenders for a theory of quantum gravity.
Hmm.
But it's all still very theoretical, right? Like no real experimental proof yet.
That's the major hurdle, yeah. String theory and loop quantum gravity, they make predictions that are, incredibly difficult, if not impossible, to actually test with our current technology. And that lack of experimental feedback, well, it kind of adds to this feeling of stagnation, right?
You've got the map, but you can't actually go and see if it leads to the treasure.
That's a good way to put it. And this issue of experimental challenges, it goes way beyond just quantum gravity. It's this broader concern in fundamental physics.
Because at the end of the day, physics is about observing and understanding the real world, not just like playing with equations on a whiteboard.
You got it. Think about some of the big breakthroughs in history, right? Galileo dropping objects from the Leaning Tower of Pisa to test gravity. Or the Michelson-Morley experiment paved the way for Einstein's theory of special relativity. These were huge discoveries, driven by experiments that actually challenged the assumptions of the time.
They forced people to look at reality, even when it didn't fit with what they thought they already knew. So how does all that relate to where physics is right now?
Well, The concern is that a lot of these modern theories, they're so abstract, so removed from our everyday experience, that they're just incredibly difficult to test through experiments. They're kind of beyond experimental reach, as the source puts it.
So we're in this situation where you've got brilliant theoretical minds coming up with these incredible ideas, but we just don't have the tools to see if they actually hold up in the real world.
That's the predicament, yeah. And it's led to this shift towards more speculative, math-heavy physics. Not that this kind of research is bad, but it does raise some concerns.
Because beauty and elegance in math don't automatically equal truth in the physical world.
Exactly. And this brings us to another point the source makes. Are physicists kind of obsessed with solving problems that might not even need solutions?
So are you saying that some of the puzzles that they're trying to solve might actually be based on the wrong assumptions in the first place?
It's a question worth asking. The source gives some interesting examples. There's the strong CP problem. It deals with a particular type of symmetry in particle physics, basically why certain interactions don't violate this symmetry when theoretically they could.
They're trying to explain why something doesn't happen. It does seem a little roundabout.
It does. And then there's the hierarchy problem, which is about this massive difference in strength between the fundamental forces. Gravity is incredibly weak compared to the electromagnetic force, for example. Some physicists see this as a problem that needs solving. Others say it might just be a fundamental fact of the universe, just a constant, something we got to accept.
I see, I see. Okay. So if some of these problems might not actually be problems, where does that leave the field? Like, what are physicists supposed to focus on, if not these puzzles?
Well, that's where the whole debate about experimental challenges really comes in. And to understand the source's argument, we're going to have to dive into a specific area of research that's gotten some criticism for being, as they say, cool, but not fundamental.
Okay, I am very intrigued. Let's unpack that. What kind of research are we talking about?
Stuff like, asymptotic symmetries, gauge gravity dualities, those sorts of things.
Oh, that sounds very complex. Can you maybe break it down for us regular folks?
Well, asymptotic symmetries, that involves looking at the behavior of physical systems at infinity, like at the event horizon of a black hole. And then gauge gravity dualities, they propose this link between gravitational theories in one dimension and quantum field theories in a lower dimension. It gets pretty complicated.
Yeah, that's a lot. But the point is, the criticism is that this research isn't getting us closer to those big fundamental questions, right?
Right? They're fascinating areas to look into, but you could see them more as like tools for refining existing theories rather than providing these huge, groundbreaking, fundamental insights.
They're like, you have all the fanciest gadgets in the workshop, but you don't know how to actually build the house.
Exactly. And the source points to another example, the amplituhedron, this geometric object that really simplifies calculations in quantum field theory, which is amazing in itself.
It's a shortcut for the math, but it doesn't actually tell us anything new about the universe.
That's the critique, yeah. It shows how brilliant theoretical physicists are, but it might not be moving the needle on these big fundamental questions that are causing this feeling of stagnation. And this leads us to an even deeper debate. Should we be focusing on directed research aimed at specific problems, or should we kind of embrace serendipity and let the math lead the way?
Planning versus exploration. That's a very interesting topic we definitely need to dig into more. But first, I think it's good to recap what we've covered so far. We started with this idea of stagnation in physics, driven by this lack of experimental data to confirm or deny some of these more out-there theories.
And we talked about the idea that some of the problems physicists are working on might not actually be problems, which raises all these interesting questions about where research should be focused.
Right, right. And we've just gone over some promising avenues for progress, both on the experimental and the theoretical side of things. Things like the LHC, that search for dark matter, and then the really amazing stuff we're learning from cosmology.
And then all those wild theoretical concepts like modified gravity, emergent gravity, even these alternative interpretations of quantum mechanics.
It's been quite the tour through cutting-edge physics. But I think it's fair to say the field isn't stagnant when it comes to creativity and the willingness to explore new ideas.
Oh, absolutely. But what does all this actually mean for us, the non-physicists who are trying to understand these incredibly complex ideas?
That's a great question. What are the implications beyond just, the world of academic physics? What can we learn from all of this that affects our everyday lives and our understanding of the universe? So we've been talking about how fundamental physics might be kind of stuck in a rut. But does that mean it's like a dead end? Are there, any glimmers of hope on the horizon? Are there any promising paths forward?
Oh, absolutely there are. Physics has a way of surprising us. It might feel like we're stuck, but that tension is exactly what leads to a huge breakthrough.
So less doom and gloom, more like, the calm before the storm. I like that. But where should we be looking for these big breakthroughs? What are the most exciting areas that are being explored right now?
Well, on the experimental side, there are some really incredible projects underway. They could provide the data we need to kind of shake things up. The Large Hadron Collider, the LHC, is constantly pushing the boundaries of what we can observe, like way down at the subatomic level.
The LHC, yeah. That's like the ultimate microscope. Didn't
Yeah.
they discover the Higgs boson there a while back?
Yeah, they did, and that was major, right? It confirmed the standard model of particle physics. But it also, brought up a whole bunch of new questions. And physicists are hoping that maybe the LHC could find evidence of something called supersymmetry, which basically predicts that there are partner particles for every particle we already know about.
Supersymmetry. That sounds like something straight out of science fiction. But how would finding those particles help with the problems we've been talking about?
Well, for one, some of those hypothetical particles, they could be candidates for dark matter. If we could actually detect them at the LHC, it would be a huge step toward understanding what this mysterious stuff is really made of.
So that's a possible connection point. If supersymmetry is real and those particles are out there, it could solve one of the biggest mysteries in physics.
Oh, it'd be a total game changer. But there are other ways to approach it experimentally. Some physicists are actually trying to detect dark matter directly, not by creating it in a collider, but by looking for how it interacts with regular matter.
So instead of making dark matter, they're trying to set traps for it.
That's the idea. They
Yeah.
use these incredibly sensitive detectors, often shielded deep underground, to get rid of background noise. And they're hoping to catch these very, very rare interactions.
That's like looking for a needle in a cosmic haystack. But I guess if you find that needle, it's worth the effort.
Totally worth it. And then you have the whole field of cosmology, right? Studying the large-scale structure of the universe, looking for clues about dark energy and the early universe.
Cosmology, I don't know, it always makes me feel really small and totally fascinated at the same time. What kind of tools are they using?
We have some amazing telescopes, like the James Webb Space Telescope, giving us these incredible views of the early universe. It's like peering back in time to when galaxies were first forming.
It's hard to even wrap your mind around that. We can actually see that far back in time. That's wild. What can we learn from that?
Well, by studying the distribution of galaxies, the cosmic microwave background radiation, all of that cosmological data, we can test our models of the universe and maybe uncover some new physics that explains things like dark energy and the accelerated expansion.
Okay, so those are some exciting things happening on the experimental side. What about theoretical physics? Are there physicists out there who are thinking outside the box, proposing, completely new ways of thinking about all this?
Oh, there are always those who are willing to, challenge the status quo. Some are exploring modifications to general relativity itself, trying to explain stuff like dark energy and dark matter without saying there are completely new particles.
So instead of adding new ingredients to the mix, they're kind of tweaking the recipe a little bit.
Exactly. There's modified Newtonian dynamics, or MOND, for example, which suggests that maybe gravity acts differently at these super large distances than we currently think.
So they're saying that maybe gravity itself works differently on a cosmic scale, and that's why we're seeing these weird gravitational effects, rather than there being all this dark matter out there.
Exactly. It's controversial, but it shows how some physicists are willing to really question our most fundamental assumptions.
Are there any other, radically different ideas that are being explored?
There's this concept called emergent gravity, which says that gravity might not actually be a fundamental force at all. It could be an emergent phenomenon, something arising from the behavior of something else, something even more fundamental.
Emergent gravity. Wow, that's almost philosophical. You're saying that gravity isn't, baked into the universe from the beginning, but it somehow emerges from something else.
Yeah, it's a mind-blowing idea, but it's gaining traction in some circles. It really challenges how we think about gravity and space-time.
I need a minute to process that one. So something we experience every day, something as basic as gravity, could be way more complex than we ever thought.
It could be. And then there are even some people who are questioning the foundations of quantum mechanics, saying that maybe we need a completely new framework to really grasp the quantum world.
Wait, they're saying quantum mechanics could be wrong? but it's been so successful at explaining so much about how the universe works.
It has been incredibly successful, yeah, you're right. But there are still those big mysteries, like the measurement problem we talked about earlier. It just baffles physicists. And some think these puzzles point to deeper problems with the theory itself.
So they're not saying that quantum mechanics is completely wrong. They just think that maybe the way we're thinking about it needs a makeover.
Yeah, that's a good way to put it. And there are a lot of interesting alternative theories that people are exploring, like Bohmian mechanics, which suggests that maybe there are these hidden variables that influence how quantum particles behave. That would make the quantum world a lot more deterministic than it seems.
Hidden variables. That's like saying there's a secret code that's
Yeah.
dictating how quantum experiments will turn out.
Yeah, exactly. It's a totally different way to think about quantum mechanics, but some physicists find it really compelling.
I love how this deep dive has taken us from like these seemingly impossible problems to all these super creative, mind-bending solutions.
It's been quite the journey, right?
It really has. And I think it shows how science isn't just about getting the right answers, it's about asking the right questions, being willing to challenge what you think you know, and really embrace the unknown.
I couldn't agree more. And so, even though fundamental physics may be going through what the source calls stagnation, it's definitely not a dead end. It's more like this fertile ground for new ideas and approaches to take root and maybe blossom into something amazing.
I'm feeling optimistic now. But before we get too carried away with all these possibilities, let's take a step back. Can we summarize what we've covered in this deep dive so far? We started with the idea that, fundamental physics might be stagnating, partly because there isn't enough experimental data to support or refute some of the more complex theories out there.
And then we got into this idea that some of the problems that physicists are focusing on, well, they might not actually be problems, which makes you wonder about where we should be focusing our research efforts.
Right, exactly. And then we just explored all these super promising avenues for progress, both experimental and theoretical. We talked about the LHC, searching for dark matter, and all the incredible things we're learning from cosmology.
And we went deep into some really mind-bending ideas like modified gravity, emergent gravity, and those alternative interpretations of quantum mechanics.
It's been a whirlwind tour of the cutting edge of physics, but I think we can say that when it comes to creativity and exploring new ideas, the field is far from stagnant.
Definitely not. But what does all of this mean for, us regular folks, the non-physicists who are just trying to understand these complex ideas?
That's a good question. What are the implications? Beyond just academic physics, what can we take away from this deep dive that affects how we think about the universe and our place in it?
One of the biggest things I'm taking away from this is just like a renewed sense of awe, just thinking about the universe and how much is out there that we still don't know. Like, even with all the advances we've made in science, there are still so many mysteries to solve.
Oh, absolutely. It's humbling and exciting at the same time. And it really makes you appreciate how hard physicists are working to try and understand all of it, pushing those boundaries of knowledge. It really does. And it makes you think about how important it is to support that research, to make sure we're funding those big, ambitious projects, the ones that could totally revolutionize how we understand the world around us.
That's a great point, because if experiments are the key to really unlocking these truths about the universe, then we need to be supporting the right kind of research, even the stuff that seems kind of out there or a little bit speculative, because those are the kinds of ideas that could lead to the biggest breakthroughs.
Right. It's so easy to get caught up in the day-to-day stuff, but we also need to be thinking about the long game, right? The future of science and knowledge.
Yeah. And this also highlights how important it is to collaborate not just between physicists, but across all different fields. We need mathematicians, computer scientists, engineers, even philosophers to really get a handle on these big questions.
It's like we're putting together a huge puzzle, and we need everyone to bring their pieces to the table.
That's a great way to think about it. And it also brings up some interesting philosophical questions, like if we do figure out how to unify quantum mechanics and general relativity, if we actually solve the mysteries of dark matter and dark energy, what does that mean for us? For how we understand our place in the universe?
Whoa, that's getting pretty deep. It's like asking, what's the meaning of it all? But I think those are important questions to wrestle with, especially as our understanding of science keeps evolving.
For sure. And it makes you wonder about the ethical side of it too, right? As we learn more and more about the universe, are we going to be able to use that knowledge wisely,
Sure.
responsibly?
That's a big one.
Okay.
It's not just about getting the knowledge, it's about what we do with it. We have to use it to benefit humanity and make sure there's a good future for everyone,
Mhm.
for us and for the planet.
Exactly. So even though this deep dive started out by asking if fundamental physics is stuck, I think we've ended up talking about so much more. Like the nature of science itself, what it means to be human in this vast universe, and how new discoveries could completely change how we understand reality.
Absolutely. It's been an incredible journey exploring these mind-blowing ideas and trying to get a grasp on these big questions that keep physicists up at night.
And I hope it's left our listeners feeling that sense of wonder, that thirst for knowledge, and that desire to keep exploring these amazing mysteries of the universe.
That's what we always hope for, We want to get people curious, start conversations, and encourage everyone to dive deeper into the things that fascinate them.
I think we've done that today. And who knows, maybe one of our listeners is going to be the one to make that next big discovery, The one
Oh,
to finally solve the mysteries that have puzzled physicists for so long.
anything's possible.
Yeah.
The next Einstein, the next Marie Curie could be out there right now listening to this and getting inspired.
And if that's you, we want to hear from you. Let us know what you think, what questions you have. We want to hear about your deep dives into the world of physics.
And until next time, stay curious, keep those imaginations going, and never stop exploring. Who knows what incredible things we'll discover next?